Welcome back to our final keynote of the day. Samir from AWS will share his insights into how to automate and optimize ML pipelines. So Samir, it's a great pleasure to have you. It's great that you have this talk. I just heard that in the AWS he's kind of a rock star, and that means a lot. And he's road tripping here, which I also think is really cool. So he took some days from Amsterdam to come here and road trip and stop at some of the nice cities on the way. So that's also like a cool way to travel. I really like it. I hand over to you. It's a pleasure to have you, and enjoy the talk.
Thank you very much. Good morning, everybody. Thank you for being here. Thank you, Martin, for inviting me. So my name is Samir. I'm an AI/ML solutions architect at Amazon Web Services. I normally work focused on machine learning model optimization for the cloud and for the edge. And today I brought two important topics when you build machine learning pipelines. So when you need to consider when you build machine learning pipelines. And a machine learning pipeline, it's basically a set of steps you need to execute in order to have a working machine learning model at the end. A machine learning model that will address a particular business challenge, right? So when you have just a few steps like data preparation, model building, model evaluation, model deployment and execution, and when you need to run these pipeline or these steps multiple times in an industrial scale, so it makes sense to talk about automation. Automate this to make it easier for the machine learning developers, for the business areas to control this pipeline and have a good product at the end. And optimization, of course, because after deploying a machine learning pipeline, you also need to optimize. It's important to optimize this pipeline. There are different ways to interpret this term. It's a generic term. So if you have multiple steps, then you can merge these steps or remove useless steps if there is any. So this is a type of optimization. But in this case, in this session, we're going to focus on a different type of optimization, more focused on the model training and model inference optimization. They are the most critical parts of your machine learning pipeline. And if you can optimize them, you are doing a good job at the end, right? And in this session, we're going to try to answer these two questions. So for automation, how to get a faster time to market? Because if you automate your machine learning pipeline, you can, and you have a new data set, you just kick off this machine learning pipeline, and in a couple of hours or eventually minutes, you have a new machine learning model in production, right? And when we talk about model training and model evaluation or model inference optimization, we are focusing on cost reductions and performance improvements. Let's talk about automation first. And there's a term called machine learning ops or MLOps. And this is a buzzword, like other buzzwords out there. So AutoML is another buzzword. But let's try to disambiguate these two words. We're going to focus on machine learning ops, which is a set of practices. This is a concept, not a technology. And then you need to bring your tooling, and we're going to see what AWS offers for you to build your own machine learning ops platform. But the idea of machine learning ops is to automate the process of building a machine learning model. So data preparation, training, evaluation, monitoring, deployment, execution. And then we have another term called AutoML. It's easy to mix these two, but they mean different things. AutoML can be contained into machine learning ops. AutoML is only about building a model. So if you don't have machine learning data scientists or machine learning experts, you can just use AutoML, which is another concept, but there are also techniques for you to automatically build your model. So you just point your AutoML mechanism to your data set. It will prepare your data, train a few models, optimize them, select the best one. So in an AutoML, in a machine learning ops pipeline, you can replace the building part of your machine learning ops by AutoML. But in this session, again, let's focus on machine learning ops. Oops. Okay, so when should I start automating my machine learning pipeline? Since the beginning, but since the beginning after the experimentation. And we're going to explore one important thing, which is if you don't, you need to have a well-defined business challenge in order to start your experimentations and start building your machine learning pipelines. So a normal set of events will be, first, you identify a business challenge, then you frame correctly this business challenge, you have an understanding, and then you start experimenting. And after building a few POCs, you can start building your automated pipelines. And by doing this, you can fail fast, and you can evolve your machine learning, your automated machine learning pipeline faster. And of course, you put an MVP in production, and then you keep evolving this quickly, right? So, but again, the business problem is the most important part of this whole process. If it is not clear in your mind, so there is a huge chance that we will build something that will be useless for you in the future. So that's why I brought here CRISP-DM. This is a very old process for mapping, data mining scenarios, but we can use here, we can borrow for machine learning. It's a classic process where it starts with this step, business understanding, the most important part of this process. And I like to work with my customers in an approach where I frame a business challenge into a question. And then my solution will be the answer for that particular question. So you start by framing your business challenge, and then you take a look at your data and see if your data is enough to answer that particular question. If it is not enough, you need to collect more data, you need to prepare a different data set, right? And then after this, you can run your machine learning pipeline, where you will prepare your data, so take your raw data, prepare your data set, train your model, evaluate, and deploy. In this model here, there are some steps that are missing, like monitoring, which is also important, data collection, logging, and other features. That normally, these additional steps, they are part of a proper machine learning ops pipeline. Okay, so I talked about the questions. So I brought here some generic questions that normally I like to use as a baseline when talking about a business challenge. So I try to classify the questions here as these types here. And then here you can ask or frame your business question, your business problem, with a more generic question, like, for instance, how can I reduce the time it takes for me to support a customer? This is a very generic question. And then you need to ask a more specific question and that is related to the problem you're trying to solve. So if my customer has a problem with a broken part, so how can this customer send me a picture of this broken part and I find the part that needs to be replaced and send to the customer? This is a more specific question. And with a more specific question, a concrete question, you can start building your machine learning pipeline, right? So there's something wrong with my slider. I will use the keyboard here. So you have your business challenge. You already understood what you need to do. You framed your question. You have the steps in mind, what you need to do. And then you start experimenting with candidate models. You use like an IDE or a Jupyter-based notebook. You explore your data. You select some models. And then you have some POCs, small POCs, like one to prepare your data, another one to train your model, another one to evaluate or run hyperparameter tuning. And then you start building your automated pipeline. These are the foundation keys for machine learning ops pipeline. I can highlight two items here. So flexibility and reusability, they are connected because after building your first MVP, you're going to put this model in production, and then we will evolve, we'll add more features, and then we'll start working in a second model, in a third model, in a fourth model, and so on. And then in the end, you have a factory of models. If you need something very flexible, something that you can basically take some templates, deploy to another model, and this template will be flexible, reusable, and generic enough for you to address any type of model. So this is a natural evolution of your machine learning environment, right? And then I brought here a maturity model. So we're here at the initial stage. You're gonna do the experimentations, like I mentioned before. You will try to understand your business challenge, but after you build your first automated machine learning ops, even a small one that will basically prepare your data, train, and run your model in batch mode, for instance. This is a very simple pipeline. You can, when you create your automated pipeline, you can see it like a function that encapsulates all these steps. You can pass some parameters to override the default ones, but you can invoke this function as many times as you need, right? And when you do this, you reach at the second level, when you can repeat this process over and over again and expect the same results if you don't change the data set. But in a real scenario, you keep changing your data set, adding more data, and so on. So, and then you evolve this by adding more features like monitoring. You keep monitoring the quality of your model. If the quality is decaying, so when you train a model, you use a metric. Can be accuracy, precision, F1 score. So it doesn't matter which metric you're using, you can keep using the same metric to evaluate your model in production. If the performance is decaying, so eventually it means that you need to retrain your model. So you keep collecting this data, sending it back to the original steps, and retrain your model. Or depending on the way your users are interacting with your model, eventually the behavior is changing. So, and you see this as a data drift in the data you're collecting. This is also part of the monitoring here. And finally, you reach the scalable, where if you're training a small computer vision model, for instance, you can run just your pipeline using just one instance. But then you need to train a GPT-3 model or a large language model, and you need a big cluster, hundreds of instances with multiple GPUs or hardware accelerators. So then you can just reuse this and just change the parameters of your machine learning pipeline, and the rest will be done for you automatically. So that's the mental model of an automated pipeline. AWS has a service called Amazon SageMaker to support the end-to-end machine learning pipeline. So I'll not dive deep into this service, but you can see SageMaker as a service where there are multiple APIs exposed to the data scientists. So they don't need to know or to take care of the infrastructure. This is a managed service, which means that they will invoke one API to train the model, passing the training script in PyTorch, TensorFlow, scikit-learn, or any framework, point the service to the data set, stored into an object store, and that's it. You pass some parameters, SageMaker will launch 1, 2, 10, hundreds of instances, depending on your parameters. Will execute your training script, you train your model, you save your trained model back to the storage and destroy the infrastructure automatically for you. And if you need to deploy this model, you basically invoke another API. The service will take your model, wrap around the Docker container, expose as an API, and then you can invoke or integrate with your backend, your application. So these are the core features. So to run a data preparation step, to train your model, to deploy your model for real time, for batch, or eventually if you need to deploy to an edge location, like a machine, a computer close to a machine, you can also integrate with other services that will take this model from the cloud and deploy to a server, a local server. right? And you also have an IDE, Jupyter-based IDE, where the data scientists can experiment, but it's very modular, and you can basically combine which APIs you're going to use. And on top of these core services, there is another feature called SageMaker Pipelines, which is a Python library that you can compose all the steps you need to run a pipeline, a machine learning pipeline, and after you execute this Python script using this SDK, you have a physical address or a physical function that you can then invoke as an API, and SageMaker will execute all these steps, the core features for you, orchestrate this under the hood for you automatically. And again, this is something that you can execute as many times as you need, passing different parameters, pointing to different data sets. And this is something that you can also integrate with other services. So for instance, you are copying a new data set to an S3 bucket or the object store. You can create an event based on this action to trigger this pipeline and retrain the model. So this is something that you can integrate with different types of mechanisms as well inside at AWS, or invoke from an external application if you need. Just an example here of a use case inspired on a use case that we worked at Festo. So you sell robots to your customers. You have multiple models, multiple versions of these models. In total, you have more than 50,000 parts. And then your customer, something went wrong there at the production, and a part of this robot is broken. The customer can just take a picture of the broken part using the mobile phone and send to Festo or to your operator. So this poor operator here needs to search in this huge database, 50,000 products, using this picture. It will be super hard for this person to identify this part. So what you can do, you can prepare a data set of parts and train a machine learning model. So in this case, a computer vision model, an object detection model that can identify a Festo part or a robot part in the picture. Then you take the crop, run the back end of the model to extract the features or the semantic information out of this part, and then you search using a second model, which is a clustering model, to identify the most similar parts based on this feature you extracted. And then you can return to the operator the top 5, top 10 parts, and then it will be way easier for this operator to identify the part and help the customer to replace. And you can express this as a SageMaker pipelines and automate this process. If you add more parts to your database, now you have 100,000 parts. It's just a matter of kicking off this training pipeline again, retrain, and you have a proper model here. So for the operator to find the new parts. Okay? Now let's talk about the machine learning model optimization. So there are two different aspects of machine learning model optimization. A trained model in the end is just a file, a data structure represented as a file. So if you consider a neural network, a deep learning model, you have a bunch of weights, or basically numbers, floating point 32 numbers represented inside this file. So if you have millions of parameters, you have a relatively small file. But when you have a large language model, foundation model, we are talking about billions of parameters. And last week, so there is a new version of Megatron that was launched with 1 tera parameters. So we were talking about billions of parameters so far, but now we have tera parameters. So these models can occupy many gigabytes of disk. So if you basically reduce the data representation from FP32 to FP16, so you are reducing from 4 bytes to 2 bytes, you're slicing your model in half. Of course, there are some you are losing some accuracy here, but it's manageable. And by having half of the data to process, you have a faster processing time. So this is one of the strategy. when you work with model structure. There are other strategies like pruning. You can remove dead parts of your model. You can run caching and other conversions you can apply. But sometimes this is not enough. This is especially important when you deploy a model to an edge computing. Normally, these edge computings, they don't have much power, so it's important to squeeze as much as possible your model before deploying. But sometimes this is not enough, especially for large language models, and then you need hardware acceleration. For which purpose? Cost reduction, and of course, improved performance. So in 2018, AWS started building its own silicon technology for Nitro systems. So Nitro systems is a series of boards that were created with some processors to offload features from the hypervisor. So when you launch virtual machines, networking, security, storage, they are now offloaded to these boards. So the users have 100% of the hardware they have, they launch it. So, and then after this, AWS started building its own technology silicon technology for other tasks. So Graviton, which is a general purpose ARM 64 bits processor, was launched in 2018, and last year the version 3 was launched, and it also has important features to accelerate machine learning models, like seamed co-processors to accelerate this type of operations. But in 2018, so we launched the first silicon technology dedicated to machine learning, so Inferentia. It's a chip to accelerate the execution of deep learning models. And last year, we launched Trainium, which is the second generation of these technologies for machine learning, but in this case, a chip to train deep learning models, more specifically to train big models, large language models, and foundation models. And it was announced last year. It is in preview right now. Will be launched soon. Inferentia 2 that shares the same technology of Trainium, the second generation of the chips. But Inferentia 2 is to execute your model. So you train your model on Trainium and deploy on Inferentia. The customer's perspective, the machine learning developer perspective, you just work with your deep learning framework. You work with PyTorch. You work with TensorFlow. And there is a driver that delegates to the hardware automatically for you, so you don't need to worry about the specificities of this hardware, right? So it's transparent, like you're using a GPU under the hood. Just out of curiosity, this is the structure of an Inferentia chip. Inside each chip, it has 4 cores, something called Neuron Core V1. This is for Inferentia 1. You have 4 independent cores per chip, and there are instances with 4 chips, and you can basically load one independent model in each one of these chips or shard your model across multiple cores. Why would you need to shard your model? If your model is too big to fit into the 8 gigabytes of accelerated memory, so you have a 16 gigabytes model, you can slice it and shard across multiple nodes, or you can increase the throughput. So you have one model, but you shard across the four cores, so you can increase the throughput of your model. Normally when you process video files or a huge amount of data. Okay? So just to take a look, this is a comparison between Inferentia 1 and G4DN, which is an instance with an NVIDIA T4 GPU. So just a highlight here. So three comparisons: object detection with YOLO V4, natural language, which is a BERT-based model, Hugging Face BERT-based model, for text classification. And the third one is image classification with a ResNet 50. So here you can see the comparison between Inf1 and G4. Just to highlight here in terms of the cost per inference. So Inf1 is 84% lower, and the throughput for image classification is almost 30% higher than a G4, which means that a GPU is a generic purpose machine. It was not built for training and accelerating machine learning models. It was created for a different purpose, and it has tons of features that are useless for machine learning workloads. So it basically increases the cost and it consumes more energy. That's why it makes sense to use a dedicated hardware that was designed for that purpose. That's why you see these differences here in cost and performance. Another use case that I'm working with a customer. So in this case, the customer trained a BERT-based model to extract the semantic information out of text. So they have a list of IPs or intellectual property, and the business challenge here is to search through a base of documents to see if there is an IP violation. If there is something similar in this document to one of the IPs, it means that there is a probability that there was an IP violation here. So what this customer did was, we worked together to train a BERT-based model on Trainium to extract the features or the semantic information of the text. The input is the text. And for each IP, they pre-processed all the IPs and extracted the vectors stored to a database. And then they have a database of documents. They slice the document into sentences, and they send each sentence to the same model, extract the vector, and then they compare these vectors and measure the similarity using a distance-based algorithm. So if the distance is too short, it means that probably there is an IP violation. And basically, this is what we've done, and this is running in production, just for you to take a look at the advantage of that. So the requirements, 12,000-ish sentences of average 128 words per minute. So we trained this model, this BERT, on SageMaker and deployed to an Inf1 6x large. It has 4 Inferentia chips. So in total, 16 neuron cores. We loaded 4 copies of the same model, and each model uses 4 cores to increase the throughput. So inside the endpoint, we have 4 independent processes or workers, and on the client side, 5 threads sending the sentences in parallel to this endpoint, reaching an average of 2.1 milliseconds per sentence. And this is the total number of processed sentences, 1.6 million sentences per hour with this cost. So in the end, way cheaper than a GPU. Okay. So let's talk about Trainium, which is the second generation. It has Neuron Core V2, and it's the same chip that powers Inferentia 2 that will be launched soon. This big monster here, so it's a server that you can launch with 16 Neuron Core V2 chips or accelerators, and the total aggregated memory is 512 gigabytes. So these models, especially for large language models, we have models with hundreds of gigabytes and eventually terabytes. So why do you need that amount of memory? To load in just one instance the model, and then you can use all the cores available there to train, to fine-tune this model, and to accelerate the processing. So it has lots of advantages when you need to train these big models. And if you need more, you can launch multiple hosts of with this server and run a distributed training across multiple hosts and multiple accelerators. This is another comparison, but at this time against 2 other types of GPUs, P3 and P4DN. So a P4DN has an NVIDIA 800, one of the most powerful GPUs out there. And each P4 instance has 8 GPUs, 8 800 GPUs. So on the left side, you can see the data types supported by Trainium and how they are configured in terms of the bits distribution. And here you can see 3 different tasks. So the comparison against of Trainium this bar here against P4 and P3 in different data types. So BF16, FP16, these 16 bits data types here, TF32, which is the second one, and FP32. FP32 is the most common data format. When you launch, by default, a training using PyTorch or TensorFlow, this is the data type you use. But it's common to, when you train these big models, to use something called mixed precision. And this is done automatically by the hardware. So internally, it converts some tensors to different data types to accelerate the process. And just let's take a look inside the Neuron Core V2, the chip that powers Trainium and Inferentia. It has an on-chip high bandwidth memory, and that can be combined across multiple chips in the same instance. And three engines, three dedicated engines. One scalar engine to just operate floating point numbers, a vector engine for operations like normalization, pooling, when you need to load a vector and apply in one cycle, you operate all the values of this vector. Tensor engine for more complex computations like convolution, reshape, transpose. But it also has 8 fully programmable SIMD coprocessors if you need to build your own operator. If you compare with CUDA, when you are building a GPU-based system, it's like your program, instead of programming CUDA, you're going to program in GPSIMD to build your own your custom operators. Okay? All right. So why this generative AI is how it is correlated with what I just said. So Trainium and Inferentia, they are powerful technologies to accelerate big models, any type of model, but more specifically these big models. And generative AI is a hot topic, especially for the large language models, the foundation models. So here you can see some of the pictures generated by Stable Diffusion, which is one of our partners. Stability AI is one of the partners of AWS, and they are migrating some samples to Trainium and to Inferentia 2 to make it easier for the customers to just launch these models. Trainium and Inferentia support like big models, Megatron, which is the equivalent to GPT-3, and other big models. So yeah, so I'm working right now with a customer that is training one of these big models for question answering to replace the chat bots. And in a better way, because the customers can interact, you can keep the context of the conversation and return more efficient questions to your customers. And there's a feature in SageMaker, the service that I mentioned, called Jumpstart. So here you can see in the Jumpstart, it's basically a template with a sample, with a Jupyter notebook, with some code that you can just press a button and launch inside SageMaker for you to start experimenting with these models out of the box. So models from Stability AI. There is Alexa also shared a big model here for these tasks. You have Hugging Face and some proprietary models like Cohere, Lighton. And but normally so ChatGPT is a buzz, and everybody wants to experiment with ChatGPT, but this is a proprietary technology. So there are compatible models like Megatron, which is compatible with GPT-3, and eventually we'll see something comparable to ChatGPT soon as an open source technology. So there are lots of things you can do with these models. And normally when you use these models, it's called also foundation model, because you can train just one model and address multiple tasks with the same model. And if you need to improve or to add more knowledge to this foundation model, you don't need to completely retrain it out from scratch. Just a few samples. So just a few samples is enough for you to fine-tune your model and make it useful for a new task. Okay? That's it. I know it's a lot of things. It's a little overwhelming, lots of information. But feel free to send me any questions if you want, or I will be around as well.